Hey guys, welcome back. We are going to continue and move forward. We're going to charge into our last section of the entire year, of the entire curriculum. It is maybe one of the most exciting ones. I think it's certainly one of the more interesting ones. It can be difficult if you try and rush into solving these problems by just sticking with a formula or just trying to, you know, kind of get your way around actually visualizing what's happening with the math here. Okay, and so you can notice here I put a bunch of just random images that you may see throughout this section, and these are the types of pictures and things of that sort that we're going to be using in order to explain how calculus can help us throughout this section itself. And so hopefully just by looking at these four random pictures, you can see that visualization and being able to really understand the theory behind this section is probably more important than it ever has been. Okay. Yes, there are going to be some easy ones today. We are starting at a very foundational level. But if you really, like I said, just try and skip through this first part, the rest is going to be really difficult. Okay, so please make sure that you understand today's lesson before you move forward, and let me know if you have questions, seek out some extra resources, whatever you might have to do. Okay, I'm going to try and start slow and just continue to build. Okay, so the first part of today's lesson is really going to be foundational, just trying to build this idea of how we can take a region, which we just finished working with in 6.1, and build a solid figure out of that region by either rotating it about an axis or using it as the base of a solid and building up from it. And so I'm going to just kind of go over exactly how we're going to do that, what's the process, our order of operations, and get into it. All right. But again, please let me know if you have questions, and just take your time with this in the beginning. The more patient you are in the beginning, the easier this is as we get into more difficult material. Okay. So here's what I'm talking about, right? Here's the general idea for today, mostly. And then a few of these pieces will lead into some future lessons. But we're going to be taking something that we actually have worked with already, right? This was section 6.1. We found the area. Well, actually, this is just integration itself. But let's count the x-axis as sort of its own function. We're going to take these regions, right? So these areas underneath a curve, and we're going to turn it into something that looks like that figure on the right-hand side, right? And so what you can see is basically what I've done is I've taken this region and I've rotated it about the x-axis. And what that has done is it's created a solid figure, right? So I want you to try and visualize this. I want you to try and visualize taking this region right here and sweeping it across, like sweeping it down all the way back around to itself. Okay, so around the x-axis, and along the way, it's sweeping out. It's creating a complete solid figure. All right, you think about like maybe those fans, right? So those fans that sort of fan out, they're like very compressed and they start to fan out, right? And so I'm collecting this like area or this volume as I go along. Another thing that I always think of when doing this, and if you ever seen those party decorations that you might get at like the dollar store or Party City or something like that, and you take them and you fold them out and they form like a sphere or like some type of shape that you hang up on the roof or something like that. That's very much so sort of what's happening here. We're taking a region, we're rotating it about an axis, and it's creating a solid figure. Our job is going to be taking something like this, turning it into this, and then finding the volume of this solid figure. Okay, so we're taking a two-dimensional region, turning it into a three-dimensional object, and then finding the volume of this solid figure. All right, that's our goal. So just a few other examples. Just again, visualization is key here, right? We're going to be taking something that looks like this. So now we're taking, a function that's in terms of y, not x, and turning it into this odd looking figure, whatever it might be, some type of vase, or I see like a game piece, like a card, a board game piece, something random like that, right? But I'm rotating this one about the y-axis now, which we'll do eventually. And then maybe this. So now this is very much so like 6.1. This is the area between two curves, right? And I can rotate this about an axis. And what would that region look like if I rotated it about an axis? It would no longer be just this complete solid figure, but it would actually be this figure that has a hole in the middle, right? So it's sort of hollow in the center. And so, what types of objects or what types of figures might look something like that? And then So just go back to this. So this is a general idea. This is actually the second method that we'll learn. So we won't get to this idea for this figure today, but we are going to take a look at this first figure, right? So how do we get from here to here and figure out the volume? That's our focus today. But just as an overall view, right, we have two main methods that we're going to focus on in the beginning. The first one's called the disk method. All right, and the difference there is that we're going to be using those for completely solid figures. So I just took a look at this figure right here, right? And again, notice that there's a hole in the middle of it, almost like a donut hole. Okay. That is going to use something called the washer method. All right. And so the biggest difference here is the disk method. And I'll explain why I'm calling it the disk and washer. But the disk method is for a completely solid figure. There's no holes. There's no, there's nothing hollow about it. It's a completely solid figure. All right. And the washer method is going to be for a figure where there's a hole inside of it. Okay. So there's something you can look directly right on through it. Okay. Almost like a hole you're looking through. All right. So again, I'll explain why we're calling this disk and washer. I just want to sort of set this up a little bit. All right. Okay. So before we move forward into actually finding the volume, again, I want to take some time setting this up. And this idea of cross sections, if you've ever heard that term before, becomes critically important to understanding how all of this works. So I want to spend some time just on this idea of what is a cross section. Okay, so this is sort of like an off to the side idea that's going to wrap back around to helping us find the volume of that solid figure. So what is a cross section? Well, I want you to think of it this way, and again, visualize this for me. I want you to take an object, okay? And I've got an example there. Let's take like a lacrosse ball, right? And let's say you took a lacrosse ball and you put it on the table, and you got a saw, right? And you cut that lacrosse ball completely in half, right? So equal halves. And then you took one of those halves and you turned the lacrosse ball inward, so you're looking at that face of the ball that you cut, right? So pick it up off the ground, say it's laying flat, and turn it towards you. What shape would you see after cutting that lacrosse ball in half? What shape is inside of the lacrosse ball? You would see a circle, right? And so that circle is called the cross section of the object of the lacrosse ball. So a lacrosse ball, actually, no matter where you cut it, so it doesn't have to be in half. It could be all the way, it could be closer to the top or closer to the bottom or sideways or whatever it might be, is always going to be a circle because it's a sphere. So all cross sections of spheres are circles. Now, of course, there'd be different cross sections for plenty of different objects. And in fact, an object could have multiple different cross sections. It just depends on what the object looks like and how where you cut it. All right. But this idea of a cross section becomes really important. All right. So make sure you understand what that means before moving forward. So we are going to explore more cross sections. So things like squares and rectangles, semicircles, triangles, things of that sort. But we're going to begin actually in an easier spot, which is circular cross sections. Okay, because again, what we're going to be doing is we're going to be taking regions, so areas that are bounded by some functions, right? So these regions that we've created, and we're going to rotate them about an axis. So again, just think about that. If I rotate something, that's a circular motion, right? So I'm rotating it about an axis. Whenever I do that, there's always going to be this circular rotation and therefore a circular cross section. Okay, so in the beginning here, we're only going to use circular cross sections, all right, which is going to make it a little bit easier on us to start setting up some of these formulas. But again, I want you to keep this idea that not all cross sections are circles. So we're not always just going to be using circles. We will be using other shapes. But and this whole idea is built off of those shapes. You have to be able to know and understand what a cross section is. But for us right now, we're going to start with circular cross sections. All right, so let's get into it. We're going to start with something called the disk method, right? And I'll explain why I'm calling the disk method in just a slide or two here. But let's start kind of where we're comfortable, which is considering a region bounded by a couple of different lines and maybe a function or two. And so in this case, it's a region that's bounded by the y-axis, the x-axis, the function y equals the square root of x. And I actually forgot one. I apologize, right? So if you're writing this down in your notes or whatever it might be, can you please put in here, in fact, let me pause the video and I'll add it. There we go. Sorry. So we've got a region bounded by the y-axis, the x-axis, the line x equals 4, which is this vertical line right here, and then the function y equals the square root of x. Okay, so I've created this region right inside of here. This is the area that I'm talking about. And what I want to do is I want to rotate this region about the x-axis. So now, again, visualization. Before we actually look at the object, what object do you see? If you were to rotate that region about the x-axis, what solid figure would it create? What do you see in your head? Do you see maybe like a cup that's solid, so it can't fill it with anything, but maybe it's just like a shape of a cup that's completely filled or completely solid? Maybe it's like a bullet, kind of like a bullet shape, something of that sort. What figure do you see? All right. Maybe you said it looks something like this, right? So this isn't the exact. I've been trying to find some images online that match up with what we're doing here. And so if I were to take this region and rotate it about the x-axis, it would look something really similar to this, right? So I've got this. You see the actual function, y equals the square root of x, on the outside here, right? So that line that I just drew, kind of, right, matches with this. All right, that is the function I'm talking about. And then I've rotated it, all right, about the x-axis, and I've created this shape. I think my lines are not helping, so I'm going to get rid of them, all right? So hopefully you're visualizing that shape. Again, if you're not, pause the video, jump on the video chat with me, or let me know so we can go over this before you move forward, okay? So now we're going to get into this idea of why we're calling it the disk method, okay? Because I'm going to create this disk. So I want to wrap this back around to this idea of the cross section, right? And so imagine taking a slice of this solid figure, just straight down the middle, right down, right? And then you open it up. What would you see? You would see a circle. In fact, you can see the circle right on the outside, right? So this cross section is really easy to see because you don't even need to cut it. It's right there on the outside. But let's say that instead of like trying to figure out the volume, like a volume formula for this random shape, which is like what we know how to do for most solid figures, let's use some of the tools we've already learned throughout this year, right? And so this is going to be really similar to when we used Riemann sums, right? So we had this function, we created rectangles underneath of it, and then we created more rectangles and thinner rectangles, and eventually an infinite number of rectangles, right? And we added up all the areas of those rectangles and gave us the area underneath the curve. That's going to be very similar to what we're doing right now. So I want you to keep that in the back of your head. But instead, this time, what I want you to visualize is I'm going to slice this figure at any point, right, from 0 to 4 or 0 to whatever value we want to go to. So that cross section is going to be a circle. And so I want you to take that two-dimensional circle and I want you to give it a little bit of depth, right? So I want you to make it into like a coin or a disc, right? So this purple shaded area in the middle here is your disc. All right, it's kind of like a coin shape, something like that. Can you find the volume of that figure if you knew all of its dimensions? So if you knew its radius, if you knew what that depth was, could you find the volume of that figure? And so hopefully you're saying to yourself, well, yeah, because that figure, that disc right there, is really just kind of like a small cylinder, right? So if I were to take that disc and kind of lay it down flat, and I had to find the volume of that disc, I'd be able to do that, I know how to find the volume of the cylinder, right? It's really just the area of the circle, so pi r squared multiplied by the height, right? That would give me the volume of any cylinder, pi r squared, which is the area, the surface area here, multiplied by however deep it is, whatever the depth is, okay? So I want you to imagine doing that. And so now imagine taking an infinite number of those cross sections, right? I want you to, sorry, I'm going to go back to this slide just so we don't get too jumbled up here. I want you to take this slice, and then I want you to move just a little bit further on the x-axis and take another slice and make another disc, and then move a little bit further on the x-axis, take another slice and make another disc. And eventually what I want you to do is say, okay, well, maybe I want that delta x to be a little bit smaller, and then a little bit smaller, and a little bit smaller. And it gets to a point where it's so small that it's really just a two-dimensional circle almost, right? It's got this smallest, infinitesimally small depth to it. Finding the volume would still be the same, right? But could you eventually just add up all of these little discs along the x-axis? And as you move forward on the x-axis, yes, the discs change, the radius changes, so on and so forth. But if you were to find the volume of each one of those discs and add up all of them, could you then find the volume of the solid? So we're going to get into that just a little bit more. All right, so let's dive into it. Let's take this one disc, right? So cross section of this circle, or cross section is a circle. We already talked about that. The area up top is pi r squared, and then so the height itself. Again, remember, because I kind of took that disc inside the figure and put it down on the ground, is delta x. Okay, so I put that up here in the top right-hand corner just to remind us, right? So delta, this is the distance that we traveled along the x-axis to give this this circle some depth to make it a cylinder or a disc, all right? So r this is the important part, okay? Because r is the distance from the axis up to the function, or just f of x itself, right? So go back to this picture a little bit. If I were to take this disc and I had to figure out the volume, or sorry, the radius from the x-axis up to the end of this purple circle. Well, the radius is just the distance from the x-axis up to the function, which is the output of the function, which is just f of x itself. So what we're going to find, and which is really nice, it's easy to work with, is that r, in this case, for this specific type of problem, is always just going to be the function. And so what we're actually doing is we're creating a an area formula for each cross section. And the area formula is going to be a of x, so the area in terms of x is pi, because pi is a constant, multiplied by the radius squared, which is just the function, f of x. And so in this particular problem, our function was the square root of x. So if I then square the square root of x, I just get x. So in fact, the area of any cross-sectional circle, right? So if you were to take the cross-sectional circle at any point along the solid figure that we created, its area would just be pi times whatever x value you sliced at. Again, if you wanted to make it into a solid figure, you would give it a little bit of depth, which means you would move it along the x-axis a little bit. So there's a delta x. So however far you moved it, I would multiply pi x times that distance, and you would give the volume of this disc or this coin, this cylinder, whatever it might be. And so let's kind of work off of that a little bit farther. So now if I know my area formula is pi x, I can start talking about the volume of this disc, right? Because what I just said, pi times x times the height is going to give me the volume. Right? Again, pause here. If you're still uncertain about what's going on, take a break, go back to a different part of the video, come ask me a question, go see a different resource, whatever it might be. This is a big part, though, for us. This is the volume of one singular disk. Remember that. So now, what was our goal, though? Our goal was to find the volume of the entire solid. And I want you to try and picture this a little bit. So it's all sides about picturing it. So imagine making, that delta x infinitely small. And then I want to create an infinite number of disks along my region, whatever my region might be. And so, no, this isn't the same figure we're working with. This is just something to kind of for you to visualize, right? So it's a different function, different region, which means it's a different figure. But this is the idea, right? What if I were to make a bunch of little disks along the way and just sort of stack them on top of each other? And if I can find the volume of those disks, which we can because we just proved it, and then add all of those volumes up, I now have the volume of the solid itself. Right. And so a visualization I like to use is this like loaf of bread, right? So if you've got a loaf of bread that's unsliced, but then you sliced it evenly and you kind of took it apart, if you were able to find the volume of each slice of bread and then put all the slices back together, you then found the volume of the solid figure, right? The entire loaf itself. It's the same idea. Maybe not as tasty, but definitely the same idea, all right, visualization wise. So let's get back to it. Let's actually find the volume of the solid. Let's finish this thing off, right? So for us, we wanted to find the volume of all the disks on 0 to 4. Okay, so that was our region. That was how we bounded our region. And then we want to add all of those disks together. So what I follow the line of thought here. The volume of a singular disk is pi times x times the height, which in our case is delta x, right? And so the volume of the entire solid is the sum of the individual disks. Well, I know how to do sums in calculus is just integrals, right? So what if I were to take the integral from 0 to 4 of pi times x times dx? That's the sum of every single disk on the interval 0 to 4 using my function, the square root of x, as the radius. This simplifies to just pi times the integral of 0 to 4 of x dx. Once I'm here, this is just really simple integration, right? Power rule, plug in 0, plug in 4, multiply by pi in the end. You get a final volume of 8 pi units squared. Okay, so again, hopefully you're kind of following that line of thought, following that that logic with the disks and how we're doing this. Okay, again, visualization is the key here. Understanding this base theory is going to help you out so much in the end. Okay, so please make sure you do that. I've got 2 more quick examples for you, and then I'm going to let you loose. All right. So in general, this is what I'm talking about. We've got a volume that's going to be equal to the integral from whatever A is to B is. So depending on the region that you're formed of your area formula. Okay. So this is not just for the disk method or the washer method. This is for the volume of any solid with any cross section. Okay. This is the big general formula I'll be talking about throughout this entire section. For us, using specifically, if I'm rotating about the x-axis, this is where this is a nice formula for us. But again, this is very specific to a specific type of problem. So don't think this is the end all be all, please. That's where students get really tripped up. But for the next example, this is going to come in handy. If you're rotating a region about the x-axis and it's using the disk method, meaning that the axis of rotation is a part of your region. Okay, so there's no distance between your axis and the region itself, then you can use this formula really nicely, all right? Because, again, the radius is always just going to be whatever the function is. And so if I square the function, multiply it by pi, integrate it from a to b, you get your volume, all right? And, again, that's because you're adding up the volumes of all those really small disks. All right, let's look at this example too. So let's consider this region. So now we've got f of x equals x squared. Taking y equals 0, which is just the x-axis, x equals 0, which is the y-axis. So it doesn't really look like that comes into play too much. And then x equals 2. All right, so this is the region I'm talking about right here. All right, this region right here. And again, I want you to sort of pause if you have to and start to visualize, well, what would this look like, right? What would this figure look like if I were to rotate it about the x-axis? And then I want you to try and find the volume of it, right? What I encourage you to do is before we go into the solution, pause the video, give it a shot, right? So just follow the steps we did last video and see how you did. Okay, let's take a look at the solution. So if I'm rotating, right, I know I have circular cross sections. I notice that the region includes the axis that I'm rotating about, right? So the region includes the x-axis, and I'm rotating it about the x-axis. That means I'm using the disk method. All right, so I'm in good shape. I'm also rotating it about the x-axis, which means I can use this really nice formula right here, because again, the radius is always just going to be the distance from the x-axis up to the function, or just the function itself. All right, let's dive in. So hopefully you were able to visualize a little bit. So this one looks different than the first one. This one almost looks like a horn of some sort, maybe something of that sort. That's what I see, like a trumpet horn kind of piece there. And so the radius in this case is going to be x squared, right? So again, remember, when I say the radius, what am I talking about? I'm talking about this distance up, right? So this distance up, whatever the distance from the x-axis up, is the radius of this cross-sectional circle along the way. And it doesn't matter where you do the cross-section, right? That's still going to be the radius. It's changing because the function is changing, but the formula stays the same throughout the entire volume, all right, which is nice. The depth of each disk, again, we're not saying, hey, I'm going to move it 2 units this way, 3 units that way. It's just, we're just using dx, right? It's just sort of this general idea. I know that I'm going to make dx really, really small. So I'm just going to have this delta x that I'm using as the depth. And eventually we know that that's going to come out in the wash when we do the integral itself, okay? So my region is ranging from 0 to 2, which means that's going to be my a and my b values, okay? And from there, I know that I'm going to have to do pi r squared. Well, my radius is just x squared. So if I square that, I get x to the 4th. So can you do the integral from 0 to 2 of x to the 4th? Yes, it's x to the 5th over 5 from 0 to 2 times pi. The 0 part would cancel out. So really it's just 2 to the 5th, which is 32 over 5 multiplied by pi units squared. All right, and that's the exact volume of this solid figure that we would have created. Okay, one more. And so this one's a little bit unique, okay, because this is an axis of rotation that's not the x-axis. So it's a little bit different, but it's not terribly different, okay? So don't think like we're getting too complicated here. But there's one major difference that you need to be aware of, right? So I drew some pictures here, so I hope they're okay. They're not going to be the best. I just drew some pictures and just kind of, I drew some and then took pictures of them and posted them on here. So I hope they're all right. But here's what we're going to do. We're going to take this region. We're going to use the parabola 3x squared plus 2. We're going to use y equals 1, which is this horizontal line, right, coming out of the y-axis. We're going to use x equals 0, which is really just the y-axis, and then x equals 1, which is this line right here. So it's this region that I've shaded in. That's the region that we're actually going to rotate about the line y equals 1. So a couple of things, right? Here's something that's the same, which is nice, is that, again, I notice that the region includes the axis of rotation. Here's y equals 1, here's y equals 1. As soon as I see that, I'm rotating about the same line or a line or an axis that is also a part of the region, I know I'm using the disk method, okay, because it's going to create this fully solid figure. All right, but the biggest difference is that I'm rotating it about y equals 1, not the x-axis. And so I have to account for the radius being a little bit different, right? Because if you think about it just from this picture alone, and we'll dive into it just a little bit more in the next slide, but just from this picture alone, the radius is going to be the distance from the x-axis up to the function. Well, the distance from here all the way to the function itself is not the same as the distance from the x-axis up to the function, which would be the output of the function. And so I'm going to have to account for this space that's in between the axis and the x-axis, which is 1 unit. All right. So think about, just for right now, what would you do to sort of alter your radius in order for this to work? All right. Also, start thinking about visualizing. What would this figure look like? How would this figure turn out? Okay. So at this point, I'm going to show you this figure again just to kind of give you a visualization, but I encourage you to pause the video and see if you can try this one on your own, right? It's a little bit of a challenge, but I'm going to go through it, but see if you got it. Okay, so here's the visualization of the figure. I know it's not great. I don't even know what this thing looks like. I'm some type of like weird bowl or something, or stool, maybe like a stool kind of like on its side that you would sit on. I don't know, something of that sort. But we're going to find the volume of it nonetheless. All right. So again, the biggest thing is that the radius is no longer just f of x. we have to figure out the distance from the axis of rotation up to the function. All right. And so I know that the distance from the x-axis up to the function is f of x. But there's a 1 unit space from the x-axis up to the axis of rotation. So I'm now going to take that distance and just subtract 1, right? So now the radius itself is going to be f of x minus 1, or 3x squared plus 2 minus 1, which is just 3x squared plus 1. So once I figured it out, once I've altered this radius, the steps are exactly the same. I can go back, I can use that formula that I talked about, because I know that the volume formula is really dependent upon the area formula. And the area for this is still a circle, so it's still pi r squared. Once I have r, it's in terms of a function. I can square this, multiply it by pi, take the integral along my interval, and solve. All right. So let's take a look at the solution. So here we go. So I've got pi from 0 to 1. That's where I cut everything off. So it was at y equals 0 to y equals 1, and then of r squared. All right, we figured out r to be 3x squared plus 1 because I subtracted 1 from 3x squared plus 2. Okay, and so here's what it would look like. Now, in this case, right, you're going to have to do a little bit more work if we're not using a calculator. So you are going to have to square the inside here by foiling. All right, don't just distribute the square. You have to foil. All right, so if we do that, we get this 9x to the fourth plus 6x squared plus 1. And from there, it's just the power rule. Okay, so from there, it's not too bad. Again, I'm not going to harp on the actual integration piece here. It actually just ends up being 7 pi in the very end, which is really nice. All right, there's 7 pi units squared. Okay, there is the first video. All right, hopefully it was successful. We really started kind of slow, which is nice, I think. Because if you start slow with this stuff, you can pick up speed really quickly. All right, so hopefully you understood what was going on. Again, if not, please let me know. I have other videos that show some animation that might help you that I can send your way, or I can just talk you through some of it. Please, please, please let me know. For homework, you've got a couple of problems, numbers 1 through 4, number 6, but I'm changing the directions for number 6. I just want you to rotate around the axis y equals 2, not the x-axis, which the book says, so don't do that. And then number 18 is a little bit of a challenge. It's similar to what we did. It's still a disk method, so on and so forth, but it's got a little bit different of an orientation, and so I want you to try number 18 as well. All right. Otherwise, I'm going to cut the video now to save on time. Please let me know if you have questions, and I'll talk to you soon.